Hello everyone, I Dr. Smita Rani Bhardia from UTD CSVTU Bhilai welcomes you on this SWAYAM course entitled Fundamentals of Physics lecture number 38. Previously we have studied about the nanophysics. Now we will study about the introduction of nanomaterials and its fabrication. What are the contents of today's topic is what is the nanomaterial, what are the basic properties of nanomaterials, preparation of nanomaterials, application of nanomaterial, different method of preparation and different method of fabrications. Conclusion, we will end it. Nanomaterials are the materials that have at least one dimension in a nanometer scale, typically ranging from 1 to 100 nanometers. At this scale, metals exhibit unique physical, chemical and biological properties that differ significantly from their bulk conductors. These distinct characteristics arises due to the increase of surface area to volume ratio and the quantum effect of that dominates at the nanoscale. What are the type of nanomaterials? First is nanoparticle. These are the solid particle which are all three dimensions in the nanoscale. Common example includes gold nanoparticle, silver nanoparticle and quantum dots. Nanoparticle can be spherical, rod shape or the irregular in shape. Nanotubes. Nanotubes are the cylindrical structure with a dimension in the nanometer range and a length that can be much larger. Carbon nanotube are the most well known example, characterized by their remarkable mechanical strength and electric conductivity. Nanowire. These are the one dimensional nanostructure with a high aspect ratio. They have potential application in electronics, photonics and sensors due to their ability to confine electron and proton. Nanosheets. Nanosheets are two-dimensional structures with thickness in a nanometer range. Graphene is the prominent example, known for its extraordinary electrical, thermal and mechanical properties. Next is nanocomposite. These are the nanomaterial composed of a nanoparticle dispersed with a matrix of another material, often to enhance mechanical, thermal or the electrical properties. Let us discuss about the properties of nanomaterial. First is large surface area. Nanomaterials have an extremely high surface area relative to their volume, which enhances their reactivity and allow for the application in catalysis and drug delivery. Quantum effect. At the nanoscale, quantum confinement effect become significant, leading to the changes in optical, electronics and magnetic properties. For example, quantum dots exhibits size dependent optical properties, making them useful in imaging and display technologies. Mechanical strength. Nanomaterials often exhibit superior mechanical properties, that is carbon nanotube for example are the stronger than the steel, yet much lighter, making them the ideal for use in composite materials. Fourth one is optical properties. Nanomaterials can exhibit unique optical properties such as surface plasmons resonance, which is observed in a metal nanoparticles like gold and silver. This makes them useful in applications such as sensors and imaging. Synthesis of nanomaterials. That is the main and basic part, that is synthesis or the fabrication of nanomaterial. First is top down approach. Firstly, we will introduce about what is top down and what the examples of top down method, then we will discuss briefly all the methods. These methods involve breaking down bulk materials into a nanoscale composite. Techniques includes lithography, milling and laser ablation. Second one is bottom up approach. These methods involve assembling materials from atomic or the molecular unit. Techniques include chemical vapor deposition, sol gel processing and self assembly. Other one is green synthesis. This approach involves the use of environmentally friendly method and materials such as plant extract. So, synthesize the nanomaterials, reducing the need for the toxic chemicals. Let's first discover about what are the applications of nanomaterial, then we will discuss about the whole process of our fabrication of nanomaterial. The first one is in the field of electronics. The nanomaterial are used in the fabrication of transistors, sensors and other electronic devices due to their ability to manipulate electron properties at the nanoscale. Medicine properties. In nanomedicine, nanomaterials are employed for the targeted drug delivery, imaging and diagnostics purpose. Nanoparticles can be engineered to carry drug directly to the cancer cell, reducing side effects, etc. Energy. In the field of energy, nanomaterials are being explored for the use in energy storage, that is like battery, like capacitors, solar cell and fuel cell. These high surface area and unique properties improve the efficiency of energy conservation and storage processes. In the field of environment, the nanomaterials are used in environmental remediation such as removing pollutant from the water and air. Their high reactivity and surface area enable efficient degradation or the adsorption of contaminations. In catalysis, nanocatalysis with their large surface area are used to accelerate the chemical reaction in the industrial processes, leading to more efficient production method. Nanomaterials represent a rapidly growing field of science and technology with the potential to revolutionize the various industries. Their unique properties derived from their nanoscale dimensions enable applications that were previously unimaginable. However, the challenges related to their safety, scalability and the regulation must be addressed to fully realize their potential. As our research continue to advance, nanomaterials are likely to play an increasingly important role in solving some of the world's most precise problems. Let's discuss the topic which is our main topic, that is synthesis or the fabrication of nanomaterials. Depending on the approach of assembling atom, ion or the molecule, splitting up bulk materials, generation of the raw materials and protocol of the nanoparticle synthesis, there are various kind of nanoparticle synthesis approach broadly. Nanoparticle synthesis can be classified into two categories, one is bottom up approach and second one is top down approach. Third one is also a synthesis, green synthesis approach, which we have already discussed a small portion of that. First we will discuss about the bottom up approach. In this approach, nanostructures are assembled from the smaller starting materials such as atom, molecule or the cluster. Short range forces like van der Waals forces, electrostatic forces and different interaction of intermolecular forces cause these atoms or the molecules to coalesce into a nanometer size particle. This bottom up technique is mostly used in the chemical synthesis of nanoparticles. The key advantage of bottom up approach are the generation of a wide range of nanoparticles with very small to large scale size and a more homogeneous particle size distribution. Generally, bottom up methods are most attractive for the both laboratory as well as industrial scale nanomaterial synthesis due to controllability in the size and properties of materials where proper control of the reaction condition. Some of the bottom up approaches of the synthesis are the following. One is sol gel method, second one is physical vapor deposition, third is chemical vapor deposition, molecular beam epicity and spray conservation process, wet chemical synthesis, self assembly and so on. Second one is mostly, we will discuss about it the further. For the second one is the top down approach. First we will introduce about, I will introduce about the top down, what is the top down approach. The size reduction techniques such as top down or the physical process are the used to produce nanostructures material from a big bulk material. The ability of synthesize a huge quantities of a material is a one benefit of the top down approach. However, this method makes it difficult to control the shape and the size. Instead of producing nanoparticles, this approach is typically useful in the synthesis of nanostructures bulk material. Some of the top down approaches for the synthesis of nanomaterials are the following: mechanical alloying, equal channel angular pressing, high pressure torsion, nanofabrication and nanolithography, and so on. The bottom up and the top down approach can be schematically represented as we presented in all these photos. Let's describe what is the top down method. First method is the sol gel method. The sol gel method is a chemical process used for the synthesizing nanomaterials, particularly metal oxide and ceramics, by transitioning material from liquid sol phase to a gelatinous gel phase. This method is a bottom up approach where the formation of an oxide network occurs through polycondensation reaction in a solution. What is the process overview? First is in the initial process, the process begins with the hydrolysis of a metal oxide such as methoxide or the ethoxide, where the epoxy group OR is replaced by hydroxy group ligand, that is OH. The hydrolyzed product undergoes the condensation reaction, leading to the formation of OX bridge as shown in our picture, and the three-dimensional solid network forms. The condensation reaction, the oligation involve the formation of M, OH and M bridge, while oxidation involve the creation of oxo bridge, that is MOM. These reaction results in the formation of condensed oxide or the hydroxide species, which extended into a solid phase network. Polymerization state, the process involves three key stages: polymerization of monomer unit, particle grown, and the formation of network that thickness into gel. Other is sol to gel transition. In an acidic medium, this transition allows the material to be molded into a various shapes such as film, fibers or the monoliths. In the basic condition, it produces a colloidal solution. The next step is drying and final product. Xerosol and aerosol. The removal of the solvent from the gel leads to the formation of xerosol or the aerosol. Xerosol typically shrink and may crack due to high interfacial tension, whereas aerosol retain their structure with the minimal shrinkage. What are the advantages of this sol gel method? The sol gel methods allow for the synthesis of high purity metal oxide nanoparticles with precise control over the chemical composition. It is a cost effective, suitable for the large scale industrial production, and capable of producing thin layer of amorphous material and geometrically shaped optical components. The method is also used in ceramic production and an intermediate layer in the various applications. The some disadvantage, or this method also have some disadvantage, and that are the primary disadvantage is the high cost of alkoxide precursors, which can limit it in economical feasibility for some applications. The sol gel method remain a versatile and the widely used technique in nanomaterial synthesis, particularly in the producing high purity and homogeneous metal oxide. We have two kind of vapor deposition. First is chemical, second one is physical. We will study only about the chemical vapor deposition. Chemical vapor deposition is also known as CVD, is a widely used bottom up method for the synthesizing thin film and nanoparticles. In CVD, gaseous precursor materials react or the decompose on a heated substrate to form a stable solid layer. Although more complex than physical vapor deposition, CVD offers advantages such as a high purity of the resulting materials and the ability to create thin film with precise properties, high yield and ease of scaling up. Let us discuss about the process overview. A reacting gas mixture is introduced with include volatile complex compounds such as SiH4, silicon chloride and carrier gases, that is hydrogen or the argon. The gases are transported to the surface of the substrate where they absorb. A series of surface catalyzed reaction occurs, leading to the nucleation and growth of a thin film. Byproducts are adsorbed and removed from the surface. The types of CVD. Thermally activated CVD uses high temperature to dissociate gaseous precursors, depositing materials on a heated substrate common in synthesis material like silicon carbide. Nano rods. Plasma enhanced CVD uses the plasma to enhance the reaction at lower temperature than thermal CVD. Allow for the deposition of materials like silicon carbide and the carbon nanotubes. What are the difference between CVD and PVD? Involve chemical reaction on the substrate surface leading to the film in formation. PVD involve a physical process like evaporation and sputtering, where the atoms or the molecule are deposited onto the substrate. What are the advantages of CVD? Produce highly pure and dense film of particles, can uniformly coat complex shapes due to its non-line of a site nature, suitable for a wide range of materials including materials, ceramics and semiconductors, metals. What are the it also has some kind of disadvantage, and that is challenges in synthesizing multi-component nanomaterials due to variation in vapor pressure and nucleation rates. The need for volatile, non-toxic and non-pyrophoric precursors in thermally activated CVD. CVD remains a critical process in material science, especially for a production of high quality thin film and nanostructure in various industrial applications. Wet chemical synthesis of nanoparticle. The next one is wet chemical synthesis. Wet chemical synthesis is a popular bottom up method for nanoparticles production due to its simplicity, versatility and cost effectiveness. This method is more advantageous than the sol gel process because it utilizes alkoxide, which are the more versatile and economical nanoparticle, are synthesized from the homogeneous solution through a various approaches including precipitation from a super saturated solution, chemical reduction and ultrasonic decomposition. First is precipitation method. In this approach, the method oxide nanoparticles are formed by the adjusting the pH of the precursor solution. For instance, the copper oxide, that is COO nanoparticles, can be synthesized by adding sodium hydroxide, that is NaOH, to the solution of a copper salt, that is copper nitrate 3H2O, and until the pH reaches 14, the resulting in the precipitation of the nanostructure that is CuO, the chemical reduction method. Metallic nanoparticles are synthesized by the reducing metal ion to their zero valent state using appropriate reduction agent. Surfactant or the capping agent are often used to prevent agglomeration. For an example, the cold nanoparticle can be produced by the reducing auric chloride with sodium citrate or the ascorbic acid. Silver nanoparticle can be similarly synthesized by the silver salt using reducing agent like sodium hydroxide. The ultrasonic method, that is high intensity ultrasonic facilities the synthesis of a nanomaterial by creating extreme condition of the temperature and pressure within the collapsing bubbles in a liquid, that is cavitation. This method is particularly used for the synthesizing small spherical nanoparticle of noble metal like gold, silver, platinum, palladium. Ultrasonic synthesis is advantageous because it does not require reducing reagent, offer fast reaction rates and produces small size nanoparticles. That is advantages of what are the advantages of wet chemical synthesis? It is simple and economical, high pure synthesized nanoparticle, uniform shape and size of the nanoparticle. Some disadvantage, it also has carried some disadvantages, and that is high reaction temperature are required. The use of surfactant is necessary to prevent the nanoparticle agglomeration. The large scale production can be the challenging. Wet chemical synthesis remains a versatile method for nanoparticle production, offer the flexibility to tailor nanoparticle size and the composition for the various chemical application. Now we will discuss about the self assembly of nanoparticle. Self assembly refers to the self assembly refers to the autonomous organization of the molecule of or the nanoparticles into well defined structure with external guidance. It is a significant bottom up method where the colloidal nanoparticle aggregate into the desired structure either chemically through complementary binding of the organic molecule, that is molecular self assembly, or the spontaneously, that is physical, driven by the thermodynamic minimization. The principle of self assembly is the self assembly process relies on the spontaneous chemical agglomeration of a colloidal particle. This process can be result in the organization of the particle into a ordered structure such as FCC, that is face centered cubic lattice, driven by the system's goal to reach a thermodynamically stable state. Self assembly can be enhanced by the applying an external force like a gravitational, conventional or the hydrodynamic forces. What are the types of the self assembly process? First is physical self assembly. It involves the agglomeration of nanoparticle driven by the thermodynamic energies minimization. Various factors like electrostatic forces, surface tension, entropic effect and substrate topography and the particle characteristic influence the final structure. While this spontaneous self assembly is a common other technique like template, assigned method or the external forces, that is electrical or the magnetic, are also used to achieve more controlled 2D and 3D structure. Second one is the chemical self assembly, uses organic or the supramolecular self assembled monolayers, that is SAMs, to guide the assembly of colloidal particles into a complex structure. SAMs consist of a hydrophilic head that attaches to a substrate and a hydrophilic tail that extended outward, forming a dense organized film on the substrate. The stability and functionalities of SAMS depends on the effective attachment to the substrate and can be used to produce ultra thin layer, biological sensor or the other functional materials. Commonly used organic monolayer includes the organosilicon compounds on the glass, alkaloids on the gold and DNA. What are the advantages of self-assembly? The first is simplicity. The process is straightforward and does not require complex equipment. The second one is cost effective. It is an inexpensive method for the fabrication of nanostructure. Versatility, self-assembling can produce various structure include 2D nanostructure, metal oxides, and what are the application? The method is used in the drug delivery, biosensor, biomedical, imaging and photocatalysis and other field due to its acceptability and efficiency. The self-assembling is a powerful method in a nanotechnology enabling the creation of complex and functional structures across its multiple scale-up with a minimal external intervention. Equal channel angular pressing. Equal channel angular pressing, also known as equal channel angular exhaustion, is a material processing technique designed to produce nanocrystalline and the ultra fine grained metals and alloy. This top down approaches to the nanomaterial synthesis generate nanometer sized gain by the applying the ultra high plastic strain to bulk or the polycrystalline materials. What are the process? The process involves the repeatability processing a material through a die and two channel meet at an angle typically around 90 degree. As the material is pressed through the die using a plunger, shear deformation occurs at the intersection of a channels leading to the formations of nano-sized grain, typically between 300 to 600 nanometer. This process does not change the cross-sectional dimensions of the material, making it a unique method to refine grain size without altering the overall shape. The die design, particularly the angles, that is phi and xi, is crucial for controlling the deformation process. What are the factor affecting? That is, first one is lubricant. Synthesis gaseous, particularly those based on the molybdenum disulfide, are commonly used to reduce frictions. Excess lubricant must be carefully managed, especially at a high temperature to avoid contaminations. Pressing temperature, the temperature must be carefully controlled to prevent the dynamic recovery, while ductile materials like aluminum and the copper can be processed at a room temperature. Harder material may require the high temperature. Pressing the parameters and die geometry, these are the critical to achieve the desired grain size and mechanical properties. Proper control ensure consistent result. Let us discuss about the advantages of ECAP. Scalability. The process can be scaled up to handle larger samples. Enhance the mechanical properties is the second advantage. ECAP significantly improve the mechanical properties of metal, significantly improve the mechanical properties of the metal such as aluminum and its alloy. The grain size reduction. Severe the plastic deformation effectively reduces the grain sizes, which is one of the main advantages of this technique. Reduced the contamination. This process minimizes the contamination, maintaining the nanoparticle purity. No consolidation step required. Unlike some other method, ECAP eliminates the need for an additional consolidation step, simplifying the process. Simplicity. ECAP is straightforward to set up and operate, making it accessibility for the research and industrial approach. Let us talk about the disadvantage of ECAP. The high extrusion forces. The process requires strong extrusion processes which can be challenging depending on the material being processed. Material limitation ECAP is more suited for the technologically plastic material, and it may be less effective for the materials that are not easily deformed. ECAP is a versatile and effective method for producing nanocrystalline and ultra-fine grain materials, offering the significant benefits in terms of mechanical properties and grain refinement. Thank you for your attention. In our next lecture, we will discuss about the carbon nanotube, about the graphene, about the quantum Hall effect, and all the carbon based nanomaterials and its fabrication techniques. Thank you so much.